Okay, exam 3 is Friday. Did you just tell him he looks like an idiot?
No,
Oh. That was mean. That was totally uncalled for. Yeah. And the topics are up through stress due to torsion in circular cross sections. So no thin-walled tubes. Well, there could be circular thin-walled tubes, but it would, for calculations, you'd use the approach of circular cross sections. So before I go on to what we're working on now, anybody have any questions related to the test?
Do you have the test? Did you create the test yet?
No.
You just do it like that?
Yep.
As far as equations we get, would it be okay if we wrote down an equation sheet and let you look at it and then used it? Or?
No, that's too much of a hassle. Okay. How about tell me what equations you want, and I'll put them on there.
Okay.
All the ones that are required.
All equations?
I have a few that I might want, like, stress due to torsion, stress due to,
Yeah.
that stuff.
That stuff will be on there for sure.
Okay.
Or I'll put it on the board if I forget.
And then calculating, like, Q for circles or something?
Yes, that'll be on there. Yes. That stuff will all be on there. Yep. I mean, the integral definition will be on there. No, not really.
How about the answer?
Gets funnier each time.
The answer is 42.
Oh, fine.
All right. So, anybody have any homework problems you got confused on or anything like that, or should we just move on?
We can do the hollow tube one.
Okay.
I mean, it's not going to be circular. Bigger stress. The what? Circular?
Yeah.
That's circular. Monday was a few different things. I can pull it up on my phone if you want me to, but it was just one of the torsions.
I don't know, you don't have questions?
Make me listen to it.
Or the same way as
I'll just do a new one, and it is a thin wall tube, but I'll just jog your memory when we get there about what you would do if it was a different cross section or whatever. The only difference is it's a different cross section. So this is all pretty much relevant to what you're going to do on the test. The only difference is when you calculate the stress due to the torque, the approach is slightly different. Okay, so let's say that we have a cantilever beam with a force of 5,000 newtons on the end, and then at the midpoint you have a couple of 2,000 newton meters, and then a downward force of 4,000 newtons. And we want to calculate the stress halfway between the midpoint and the wall. It also has a weight. So let's say the mass is 50 kilograms. And the cross section looks like this. So it's a thin-walled rectangular tube. The wall thickness is the same everywhere. And that wall thickness is 0.003 meters. The height is 5 centimeters. And the width is 2 centimeters. And we want to calculate the stress, so if this is the center line, we want to calculate the stress in the wall halfway between the center line and the top, and over on the right side. And this is looking at it from the wall side, so the z-axis is that way, the y-axis is this way. So first, what's the stress tensor at this point A? Call that A. And then calculate the principal stress tensor. And then the max shear stress. Okay. So to do part A, which is by far the majority of this problem, we need to calculate the internal loads at that red line. And then, based on those internal loads, we're going to calculate the stress at A due to tension, bending moment, shear force, and torque. Then we're going to add all those up, and that'll give us our total stress tensor. Okay, so I'm going to take a cut at A instead of calculating the internal loads as a function of x. So we have 5,000 newtons there. At the midpoint, we have the weight of, okay, so the total weight is 490.5. Our cut is 3/4 of that weight, so the total force is 367.875. What? That's just the weight. And then there are the two applied external loads, and those are 2/3 of the way along our cut. So there's the first one, that's the couple of 2,000. And the second one is a downward force of 4,000. And that's all the external loads.
Can you give us a range?
It's 1 meter. Would there be a length that didn't make sense? Yeah, like imaginary. That does not make sense.
The length of I.
Yeah. And then T, V, and M. And then the torque, fancy T. So Newton's second law says 5,000 0 plus 0 negative 367.875 plus 0 negative 4,000 plus t negative v is zeros. And you get that t is equal to negative 5,000. And v is equal to positive negative 4, 3, 6, 7.375. What?
8.875?
Yeah, that would. I think it's actually. That's weird. Let's pretend that this is a 3. Okay, because then I have the numbers. That comes from taking, the total weight is 490.5, and our cut is 3/4 of the beam. Or another way to think about it is, the distributed load is 490.5, and then multiply that by x to get the point force. And x in this case is 0.75. And then the moment equation about the z-axis. Okay, so what do we have? The 367.375 now has a moment arm of, so that's at the midpoint, so it has a moment arm of 0.375. Oh, that's why I messed that up, I'll bet, in the first place. The force is 367.375, plus or minus 0.5 newtons. It's like an error bar. And is that positive or negative? It's clockwise, so it's negative, yep. And then the 4,000, what's its moment arm? 0.5. And is that positive or negative? Okay. And then plus m minus vx is equal to 0. Yeah, x is 0.75. So m is equal to negative 1137.58. This is Newton meters. These are newtons. And then the moment equation about the x-axis. The only moments about the x-axis are the negative 2,000 and the positive fancy t. So fancy t, the internal torque, is equal to positive 2,000. And that's also Newton meters. Okay, so now we have all the internal loads. And so now we just have to calculate the stresses. The total stress tensor is equal to the stress tensor due to tension plus the stress tensor due to, let's do bending moment next, plus stress tensor due to shear force, plus stress tensor due to torque. And actually a rectangular thin-walled cross-section is the only one that I can think of where you can have points that have non-zero stresses for each one of those 4. We can't do it for circular cross-sections. We can't do it for solid rectangular cross-sections. I think this is the only one.
Solid rectangular
That's right. That's what we can't do, is torque. Bless you. Okay, so let's start with tension. This is a good one to warm up on. This is the easy one. So the XX stress is equal to, that's right. So our tension is negative 5,000. Our cross-sectional area, oh, this is a little bit of a nuisance. Okay, so divided by area. And so how are we going to calculate that area? So let's say that, let's do it like this. The area is equal to the big area minus the inner area. Area outer minus area inner. So that's 0.05 times 0.02 minus for the inner area, the length is 0.05 minus 2 times 0.003, right? You have one on each side. And the inner area is 0.02 minus 2 times 0.003. So you get 0.044 times 0.014. And if you calculate that, I think what you get is, where did I do that? 3.84 times 10 to the minus 1, 2, 3, 4, minus 4. So the XX stress is equal to negative 1.302 times 10 to the 7th pascals. Again, demonstrating total contempt for the rules of significant figures. And so then the stress tensor due to tension is negative 1.302 times 10 to the 7th, and zeros everywhere else. And that's pascals. Okay, so now bending. So we know that the XX stress is going to be equal to negative my over I. So we have to calculate that area moment of inertia. The area moment of inertia is equal to the area moment of inertia of the outer rectangle minus the area moment of inertia of the inner rectangle. And the reason we can just subtract it is because they have the same neutral axis. They have the same, their centroids are in the same spot. So this is 1/12 times the outer base, so 0.02, times the outer height cubed, and then minus 1/12 times 0.014, that's the inner base, times the inner height cubed, 0.044. And I think you get 1.08952 times 10 to the minus 7. All of a sudden we have like 8 significant figures. Okay, so yeah, exactly. I know. But I feel like since you guys have to take chemistry from these people who care so much about it. That's why I can just ignore it, you know. If there weren't chemistry professors out there, then I'd feel like it was my job, you know.
But since there are professors,
Right, right. Is he pretty?
He actually gave us a lecture and liked him during the lab.
Okay, good. Well, we fill gaps then. We work together as a team. Okay, so we have negative, and then the bending moment at the point that we're looking at is negative 1137.58. What's the y for the point we're looking at? So yeah, it's the distance from the neutral axis, vertical distance from the neutral axis to the point. This whole thing is 0.025, you know. Yeah. So, right, 0.025 is the whole height from the neutral axis, and so to A is 0.0125. .0125. And then divide by I, 1.08952 times 10 to the minus 7. And we get positive 1.305 times 10 to the 8th pascals. And so the stress tensor is equal to 1.305 times 10 to the 8th, 0, 0, 0, 0, 0, 0, 0. Derek's also really like obsessive about making you do everything symbolically until the end. I'm just like, I don't know. If you have round off error, you didn't punch in enough digits. That's my attitude.
Or too many.
Okay, so this is the one due to bending.
And like labeling where things are happening on your diagrams.
Oh.
Instead of just having us guess which points it's at.
Oh, yeah, right. Yeah, I think you should just guess. Yeah. You got to be able to eyeball those angles. With the angles, I always intend to label. I just sometimes forget. The midpoints thing, I might abuse. Like this is the midpoint of the midpoint of the midpoint of. Just assume that that's. Okay, so shear force. So the XY shear stress is equal to negative V times Q over area moment of inertia times B. So we have to calculate that Q, and this is going to be a bit of a pain. Q is equal to the area above the line that we're looking at. So it's that area times the distance from the neutral axis to, oh, and it's not that area. That's why it's going to be so complicated. It's going to be that area. Times the, right, times the distance from the neutral axis to the centroid of this shape, which is going to be up here somewhere. So this is the distance D, and that shaded region is the area A. and Q is equal to A times D. Okay, so for that A, I'm going to calculate the area of, as if this was a solid rectangle, and then subtract the inner rectangle area from it. So A is equal to, if that shaded area was filled all the way in, that was a solid rectangle, this would be 0.0125, that's the height, times the width. And then the area of the inner rectangle that we're removing is 0.0095 times 0.014. Okay, so 0.0095, that is 0.0125 minus 0.003. And you get an area that's equal to 1.17 times 10 to the minus 4. And now we have to calculate the location of that centroid. And we can skip the x one. We know, well, we don't care about the x. I'm saying x. I mean horizontal. Like we don't care about the horizontal position of this centroid. We only care about the vertical position of this centroid. So let's just go the y centroid is equal to 1 over the total area Stop me on this one if you get confused. I know none of this stuff is that hard to think through, but if I go too fast for you to follow it, let me know.
Start the film over.
I just meant this part if I go too fast. It's okay if I went too fast on the earlier parts. Okay. So 1 over the area times the area of the outer rectangle times its centroid minus the area of the inner rectangle times its centroid. We're just doing a centroid calculation. So we have 2.5 times 10 to the minus 4 times the centroid of the big solid rectangle would be 0.01875. And then subtract the area of the removed rectangle, 1.33 times 10 to the minus 4 times its centroid, 0.01725. And you get a value of 0.0205. And that's the distance from the neutral axis to the centroid of the shaded shape. Okay, so Q is equal to that area times that distance and you get 2.393 times 10 to the minus 6. And what are the units for Q? Yeah, that's right. Any questions? Okay, so what's B here? No, it's not. So it's actually the material. It's the amount of material you have there. So it's actually 0.006. And so the XY stress is equal to negative times the shear force, which is negative 4367.375, times the Q value that we just calculated, 2.393 times 10 to the minus 6. Divided by I that we calculated before, 1.08952 times 10 to the minus 7, divided by B, 0.006. And you get a value of positive 1.599 times 10 to the 7 pascals. So the stress tensor due to shear force is 0, positive 1.599 times 10 to the 7th, 0, positive 1.599 times 10 to the 7th, 0, 0, 0, 0, 0 pascals. Yes?
Wouldn't, I guess I'm confused, isn't B, wouldn't it be a thickness, and wouldn't the thickness be 0.003?
There's two of them. Yep. So you can think of it as that's like it's being used as a measure of the total amount of area resisting that shearing. And so if you think, so I don't know if I should even. Let's see here. Okay, so that XY shear stress is also causing, because of the requirements of a stress element, it's also causing shear stresses like this. And how much of that total, how much area that total shearing force is spread across is determined by the total material area on this whole section. So you have to take into account this length and this length. They're both contributing to decreasing that amount of stress. Okay. Okay, so the last one is torsion. This is for a thin-walled tube, so we're going to use a different formula, but the idea of the coordinate system transformations and everything, all that is the same. It's just a different formula we're using. So the formula we're going to use says that in our capital coordinate system, where the z-axis is pointing to our desired point, the XY shear stress is equal to negative torque over 2 times the wall thickness times the area of the median of the wall. The area of the median, okay, so this is sort of an exaggerated picture. The walls are really thinner than this, but So this is the area that we want.
Including the column chart too?
Yep, just the area inside, the entire area inside a line that goes through the median of the wall. So the way to calculate that, if the whole height is 0.05, this is the height minus half of the wall thickness on this side and half of the wall thickness on this side. So you get a total height of this shaded rectangle of 0.05 minus 0.003. And the same thing for the width. That's 0.02 minus 0.003. And so you get a median area of 7.99 times 10 to the minus 4 meters squared. And I don't want to spend too much time mentioning this, but when you look at a formula like this, you kind of, you think maybe you should be able to make some kind of sense out of it. Like you were just saying, Vadim, like why is that the whole area on the inside? And the fact is, the way this formula comes up is so much rearrangement of terms and then regrouping terms into things that are easy to remember and whatever, that there's really no easy way to go from how this is derived to why that's the median area. It comes from all these calculations that were done before and regrouped. So yeah, a lot of these formulas, I think, they don't make any real apparent sense.
So basically we just have to go with it.
You just have to go with it, yeah. Or you're welcome to go through the derivation. And in a way, going through derivations like that can help you remember under what conditions this formula applies. I think that's the best reason to go through derivations. But it is just sort of long and tedious, and the formulas that come out don't really bear any resemblance to the process that got you there. Things cancel, things group, and you end up with these funny looking terms. But if anyone wants to see any of those derivations, let me know, and I can loan you a book and point you to it.
I'm sure they're on YouTube.
Yeah, that's probably true. Doesn't that seem funny that it's like, you're like, oh, I'm sure it's like on a server somewhere in Seattle. I'll just look there instead of just walking up to your office. Okay, so there's the median area. And so we have everything else. So our tau, capital X, capital Y, is equal to negative. The torque is 2,000 divided by 2 times the wall thickness, 0.003. And that one, notice that is a single wall thickness. That's not the whole way across. So notice that's how it is. And then the median area, 7.99 times 10 to the minus 4. And you get a value of negative 4.172 times 10 to the 8th pascals. And so in our wacky coordinate system, our capital coordinate system, that's oriented like this, where this is capital Z, and this is capital Y, and this is our point A.
So it always has to go that way instead of actually
points.
Yeah, it doesn't actually, right. That's right.
It doesn't have to point towards the point.
It points normal to the wall that the point is on.
Okay. Well, it's a circle, it points like directly at.
That's right. Because of the, yeah, think of, so, points normal to the wall. That the point is on. Yeah, we don't have a way to do the corner.
Nobody knows.
Yeah. I mean,
You're welcome to do the research.
Leave that to the experts.
really, because of the sharp angle there, you're going to have stress concentrations, and so no calculations that we can do are going to be accurate at the corners. So just don't worry about that. And if you needed to know something at the corner, you'd have to use a more complicated approach, probably finite elements.
Does it get, I mean, this is an approximation of what we're doing, right?
Right.
Does it get less accurate the closer?
I would guess so. I don't know that for sure, but yeah, that would be my strong hunch.
Basically, if you see that kind of problem, just follow it.
Yeah. If you need to know that, then you probably have to use finite elements. And so, tau, capital X, capital Y, is equal to negative 4.1. Did I already write that? Yes. So let's just do the stress tensor here. So the stress tensor due to torsion in the capital coordinate system is 0, negative 4.172 times 10 to the 8th, 0, negative 4.172 times 10 to the 8th, and then zeros everywhere else. And now in order to add this to the other ones, we have to represent this in our usual coordinate system. So we want to go from this capital coordinate system to this coordinate system, where that's lowercase y, that's lowercase z. So what's the angle?
180.
Yeah, 180 or negative 180. With 180, it's the same either way. And then the stress tensor due to torsion is equal to Q times the stress tensor due to torsion in the capital coordinate system times Q transpose. And with 180, that just switches the signs of those. So you get 0, 4.172 times 10 to the 8th, 0, 4.172 times 10 to the 8th, 0, 0, 0, 0, 0 in pascals. And then just add them up. Add them up. And you get a final stress tensor that's equal to 1.175 times 10 to the 8th. 4.332 times 10 to the 8th. 0. 4.332 times 10 to the 8th. And then zeros. Okay, so that's part A. We have 2 parts left to go. But for part B, we want the principal stresses. So just take the eigenvalues of this and you get 4.959 times 10 to the 8th, negative 3.784 times 10 to the 8th, and 0. And so for a principal stress tensor, you can put those in any order along the diagonals. So I'll write this as 4.959 times 10 to the 8th. Then the YY is negative 3.784 times 10 to the 8th, and then zeros. It mattered, when it mattered was when we were trying to draw the coordinate system that went along with it. And then we had to be careful about whether we needed x cross y to be equal to z, and we needed to satisfy those. But this always works. You can always put those in any order. It's figuring out how the coordinate system's oriented to match those that's a little bit of a nuisance. It's not that bad. I mean, we know that, so we know that this is in our new, this is on our new x face, this is on our new y face, this is on our new z face. It's just trying to draw that coordinate system in the old coordinate system that was a little bit of a nuisance. And then the last thing is calculating the maximum shear stress. Since we don't care, I didn't ask for a tensor, it's easy to just calculate that maximum value. So it's the maximum, 4.959 times 10 to the 8th, minus the minimum, 3.784 times 10 to the 8th, divided by 2, and you get a value of 4.372 times 10 to the 8th pascals. Yep.
So if we did it the other way, we rotated it 45 degrees around one of the axes.
Yeah.
Would we have to know which one corresponds to x, y, z then?
Well, it always corresponds to, I mean, this always is x, this always is y, and this always is z. So your middle one would be z in this case, and you do 45 degrees about z.
But if we just swap like the 4.9 and put it in the z spot, then we rotate it around the x?
You do it about whichever one had the 0, whichever one had the middle of those three. Yep. So if your 0 was at x, you'd rotate 45 degrees about the x-axis, and you'd get a stress tensor that had a shear value of either this or the negative of this. Any other questions?
I'm going to have time for our quiz.
30 seconds.
Oh, I didn't write a quiz. That's the only reason you stayed.
You just told us that you knew there was going to be no quiz.
Yeah. What?
You knew there was going to be no quiz when I asked that one. Okay.
I have never known what was going to happen 2 days later in my whole life. Okay, so
That's kind of a skill.
okay, test on Friday. Think of that as like a big quiz.
You just said you've never known what's going to happen 2 days later.
Well, now that's 1 day and 23 hours from now. Now I know.
So, I was just, so let's say we